This study focused on the relationship between total rainfall and mean relative humidity, which are important climatic elements influencing environmental conditions and agricultural activities. Rainfall directly affects moisture availability, while relative humidity reflects the amount of the water vapor in the air. Understanding how these two variables are related can help improve weather prediction and agricultural planning. The objective of this study are to identify the relationship between rainfall and humidity, to develop a linear regression model that explains this relationship, and finally to use the model to predict mean relative humidity based on rainfall data. This study is significant to several groups. For the community, especially farmers, understanding how rainfall influences humidity helps in planning agricultural activities and managing water resources more effectively. From an environmental perspective, the study improves understanding of climatic interactions and supports better monitoring of droughts or heavy rainfall events. In terms of knowledge contribution, this study enhances scientific understanding of the relationship between rainfall and humidity, and shows how linear regression can be applied as a useful tool in environmental data analysis. Despite its usefulness, this study has several limitations. The dataset covers only specific months or years, which may not fully represent long-term climate trends. Additionally, other important climatic factors such as temperature, wind speed, and atmospheric pressure were not included, even though they can influence humidity. Time constraints may also affect data collection and model development. Since secondary data were used, measurement errors could impact accuracy. Finally, the use of linear regression assumes a linear relationship, whereas in reality the relationship may be complex.
For Chapter 2, we begin with data description. This study uses secondary numerical data consisting of 25 paired observations. Our independent variable x is total rainfall measured in millimeters, and our dependent variable y is mean relative humidity measured in percentage. The data is continuous and suitable for statistical analysis. Before we analyze the data, we check for the data quality. Firstly, there were no missing values, so the data set is complete. Secondly, there were no serious outliers, meaning the data is consistent. Then, we tested for normality using histogram shape and skewness. The guideline is, if skewness is between -1 and +1, the data is considered approximately normal. If it is outside this range, the data is not normal. In our dataset, both rainfall and humidity have skewness within ±1. This means the data is approximately normal, so we are allowed to use parametric analysis, including Pearson correlation and linear regression. Therefore, our data is valid and ready to be analyzed. For the graphical technique, we use a scatter plot. The x-axis represents total rainfall in millimeters, and the y-axis represents mean relative humidity in percentage. A scatter plot is chosen because it is the most suitable graph to show the relationship between two continuous numerical variables. From this graph, we can clearly see the direction of relationship, whether it is positive or negative, the strength of the pattern, whether the dots are close or spread out, the linearity, which is important to decide if regression can be used, and also if there are any outliers. Each dot in the scatter plot represents one rainfall humidity pair. We also add a trend line and the equation of the line y equal to a plus bx shows how humidity changes when the rainfall increases. The r-squared value tells how much of humidity can be explained by rainfall. From our scatter plot, we can observe that most of the dots move upward, which shows a positive relationship between rainfall and humidity. This means when rainfall increases, humidity also increases. Several numerical techniques are used to analyze the dataset. First, descriptive statistics are used to summarize the data. Mean is calculated using the formula sum of x divided by n, where x represents each data value and n is the number of observations. The median is the middle value when the data is arranged in order, while the mode is the most frequent value. However, in this dataset, there is no repeated value, so the mode is not applicable. To measure data spread, the range is obtained by subtracting the minimum value from the maximum value. The variance given by the formula s squared equal to sum of x minus mean squared divided by n minus 1 shows how far data values deviate from the mean, and the standard deviation is the square root of variance, indicating how spread out the data is. Quartiles Q1, Q2, Q3 are also used to describe data distribution, while skewness helps checks data normality, where a skewness value between -1 and +1 indicates normal data, allowing parametric analysis. Next, Pearson correlation analysis is used to measure the strength and direction of the relationship between rainfall and humidity using the standard Pearson R formula. A value close to +1 indicates a strong positive relationship. A value close to -1 indicates a strong negative relationship, while a value near 0 shows weak or no relationship. The p-value is also considered, where p less than 0.05 means the relationship is statistically significant. Finally, simple linear regression analysis is applied to determine whether rainfall can predict humidity. The regression model used is y equal to a plus bx, where y is humidity and x is rainfall. A is the intercept and b is the slope that shows how much humidity changes for every unit increase in rainfall. The r-squared value is used to identify how much of humidity is explained by rainfall, while the p-value determines whether the regression model is statistically valid. P less than 0.05 indicates a significant model. Overall, these numerical techniques help describe the data, evaluate the relationship, and determine the predictive ability of rainfall on humidity.
So this is our dataset for this research. Test of normality. To ensure the validity of our subsequent analysis, we first conducted test of normality on our two primary variables, total rainfall and mean relative humidity. Looking at the Shapiro-Wilk test, which is highly reliable for our sample size of 25, we see significance value of 1.372 and 1.378 respectively. Since both are well above the 0.05 threshold, we fail to reject the null hypothesis. This is supported by the QQ plots where data points closely follow the diagonal line confirm that our data is normally distributed and suitable for our parametric testing. Scatter diagram. Before running the numbers, we visualize the relationship. The scatter diagram clearly illustrates a strong linear upward trend. As the total rainfall on the x-axis increases, there is a visible and consistent increase in the mean relative humidity on the y-axis. Except from one minor outlier near the 4,000 mm mark, the data point cluster tightly along a potential trend line. Descriptive statistic analysis. Moving on to the descriptive overview of our data, our 25-day sample show an average total rainfall of 2,672.04 mm and a mean relative humidity of 83.77%. It's worth noting the standard deviation for rainfall is 640.86 mm, indicating considerable variability in precipitation level during the study period. For humidity, the range is relatively tight at 12%, suggesting a consistently humid environment. Correlation analysis. To quantify the visual trend, we perform a baseline correlation analysis. The result are striking. We found a correlation coefficient R of 0.983. This represents an extremely strong positive correlation. The p-value is less than 0.001, meaning this relationship is statistically significant at the 99% confidence level. Essentially, as rainfall increases, humidity follows suit almost perfectly. Model summary. Next, we look at the model summary for our regression. The R-square value is 0.966. This is a very powerful finding as it tells us that 96.6% of the variation in relative humidity can be explained by total rainfall alone. Only a tiny fraction, about 3.4%, is influenced by other external factors not included in this specific model. ANOVA. The ANOVA table further validates the strength of our model. With an F statistic of 658.344 at a significance level of less than 0.001, we confidently state that our regression model is significant fit for the data. The model is not just a result of chance, it is highly reliable predictor. Regression coefficients. Here we see the actual mathematical equation for our model. Based on the unstandardized coefficient, our constant is 60.018 and our slope is 0.006. This gives us the regression equation y equal to 60.018 plus 0.066. In practical terms, this means that even with zero rainfall, the baseline humidity is roughly 60%. And for every additional millimeter of rain, the humidity increased by 0.06%. Scatter diagram with regression line. When we overlay our regression line onto the scatter plot, we can see exactly how well the model fits. The line y equal to 60.018 plus 0.006x cuts through the heart of the data. This visual confirms that simple linear regression is an excellent tool for predicting humidity level based on rainfall total in this dataset. In conclusion, our study successfully demonstrated a strong, significant positive relationship between rainfall and humidity. Our findings showing that rainfall explains nearly 97% of humidity variance align perfectly with established climate science. These results are particularly valuable for environment monitoring, agriculture planning, and localized weather-related decision-making. Recommendations. Finally, for future research, we recommend 3 key improvements. First, expanding the sample size over longer periods to reduce bias. Second, integrating more diverse data sources like the Malaysian Meteorological Department or satellite-based database. And finally, including multiple geographic regions to see if this specific mathematical relationship holds true across different climate conditions. This is the list of references for our research. That's all from us. Bye.